Well, thank you. My name is Mai. As Nicolas said, I'm working at Flowers team at Insta Paris, also affiliated at INRIA, and I'm also at IMT Atlantic. And I would like first to thank you, organizers, Miguel and Nicolas, for inviting me to this first edition of the Latin American Summer School of Cognitive Robotics. Today I'm going to try to explain to you how robots can discover the hierarchy of tasks with intrinsic motivation to enable transfer learning in curriculum learning. So in the title, there are a lot of keywords that I'd like first to explain. What do I mean first by hierarchy of tasks? Let's try to consider this setup here, where we have a robot arm that can move around, move its at the end of its tip, but it also can grab a pen and do some drawings on a table. It can also happen to push a joystick, and through the joystick, it can control the exposition of the man on the screen on computer game. And with this green joystick, it can control the Y position of this character. So here is an example of a task that can be done by a robot, but they are related. Like, to be able to do a drawing, it needs first to know how to move around the pen. And to be able to move the pen, it needs first to be able to grab the pen, so go and take it, and then move its own arm to know where it's going. And the same goes to be able to play a video game, control a character. It needs first to be able to control a joystick. And before being able to control the joystick, it needs first to be able to touch and grab the joystick and then move its arm to move the joystick around. And each of those tasks can therefore be translated into an action that controls the different joints of the arm. And therefore, to solve the task of playing a video game or drawing a letter, then it can also use a succession, a sequence of actions. This does not only apply to robotic arms, it can also apply to mobile robots. Here we have a mobile robot, the gray one here, that can move around the room. It can see that there are green objects, and these green objects, it can move them. But there are also walls and red objects that are obstacles it cannot move. The robot can learn to control its own position to move around the room, but it can also learn to move the objects, to push objects. And once it has mastered this task of moving objects, it can use one object to push another. So this one is a more hierarchical task. So you've seen yesterday reinforcement learning, right? How robots can learn by trial and error and receive rewards. Well, a special case when we learn multiple tasks and when tasks are related to each other, they are decompositions of each other, is called hierarchical reinforcement learning. So we're going to look into hierarchical reinforcement learning today. The second keyword is transfer learning. So in machine learning, one of the most popular fields in machine learning is supervised learning, which relies on a data set, a huge data set that you feed to your algorithm, and it crunches all this data together to find the right parameters for the model. The traditional supervised learning works well when you have a lot of data, but it breaks down when you do not have sufficient data for the desired task or domain to train a reliable model. So the idea of transfer learning is to allow us to deal with this scenario by leveraging the data of some related task or domain known as source task or source domain. So instead of training a whole system on your data, because you don't have enough data, you look for a similar task or similar situation where you have a lot of data. And then you train, and then you try to adapt to the task or data or domain that you're interested in. The idea is that the experience gained in learning to perform one task can help improve learning performance in a related but different task. The insight behind transfer learning is the generalization may occur not only within task, but also across task. So if we take, for instance, this setup where it needs to be able to predict, given all the sensory motor data that it has, the reading of its slider, the position of the object compared to it, the size and the color of the object. If it gives a command to its will, what will be the positions of the objects? So it needs to learn this model M2. Let's say we have a neural network. What are the weights of these neural networks? And this is another task, which is the model M1. We have another neural network to learn this. And because this happens more often to find just one object instead of two together, we have a much larger amount of data, and we can learn M1 much easier. So the question of transfer learning is how we can transfer the parameters or the weights of the neural network, for instance. So how can we transfer these features of this model, M1, to the more difficult one, M2? So in this talk, I'm going to explain how we can use the knowledge acquired from a simple task to solve more complex tasks or a task of higher level of hierarchy. The third keyword is curriculum learning. So we talk mostly about curriculum learning in lifelong learning or continual learning. So these are two terms that mean more or less the same. The idea is that in lifelong learning or curriculum learning, we don't want our artificial intelligence to be specific to one task and one situation. We want it to be able to solve the different tasks as they come, because the needs of the users change, because the environment changes, so the robot needs to learn continuously. If I had a robot 20 years ago, it doesn't know what a smartphone is. Now it has to know in my home how to clean the smart home and take care of it, for instance. To do that, we can also try to get inspiration in cognitive robotics from biological agents. And how do biological agents do to learn all these tasks? Do you go up to a baby, a 1-year-old baby, and try to teach it to do, I don't know, to program in Python, a convolutional neural network? No, you would first try to teach it how first to grab a keyboard or push buttons on the keyboards. So the idea here is that the learning agent should be starting small with simpler tasks before trying to learn more complex tasks, as Elman stated. And this has been coined as curriculum learning by Bengio. So the idea of curriculum learning is that we need a program, a learning program, and we need to start by small, simple tasks before growing to complex tasks. And this can be done by your teachers when you attend university and school, but it can also be learned by the robot itself. It chooses by itself to learn simple tasks before going to more complex tasks. So to summarize, the robot needs to decide for each time step which tasks it needs to learn to control. So what is the goal, the purpose, and then which actions to try, so which means it needs to develop to reach its goal. This can be done within the reinforcement learning framework by trial and error, etc. So these ideas come from the inspiration that we get from biological agents. And if we look at biological agents like babies, we see that they play a lot by themselves. And through this learning, they don't go to school, but they play all the time between 0 and 6 years. But still, they learn a lot. They just grow from a crying eating and sleeping baby when they are born to almost adult at 6 years who can tell stories, walk by itself, clean itself, interact with others, do tasks, help out doing chores at home, etc. So the learning happens a lot through autonomous learning, autonomous exploration. And one of the frameworks of learning that you saw yesterday and that we will use today is reinforcement learning. Specifically for control learning within the reinforcement learning, a few works that I've cited here have been quite successful to control a robot. But you see in this picture, for instance, that this baby is playing with this ball. The question that we can ask is, why is it playing with this ball, this green ball, instead of all any other toys that are around it? They are all colorful, they make a lot of noise, they are playful. So why choose this one? And actually, most of the time, it's the choice of the kid itself. It's not the parents who tell them at every moment which toy to play with. And well, developmental psychologists have proposed explanation with the theory called intrinsic motivation, or the theory to explain curiosity. They say that children and adults actually will engage in activities or objects, toys, hobbies or plays that are at right level of complexity. These hobbies are not too easy or else they get bored, but not too complex because or else they would find it too difficult and they would get bored too. And most of the time they choose it by themselves without any reward of food, of money. We all choose hobbies that we will enjoy without any external reward. And this choice is done by us, robot learning algorithms. And Rolf and Baroness, for instance, among others, have proposed algorithms for goal-oriented learning of inverse models. This word means that it learns the control model, so to choose an action, to solve a task, and they choose this task using intrinsic motivation. So these methods of autonomous exploration have developed and have proven very successful. Autonomous exploration independent of human effort. So the robot explores by itself in its environment and learns by itself. The human doesn't need to intervene to specify a reward function. It doesn't need reward shaping, for instance. And the reward function, I'll explain later, is done internally in the system. The second advantage is the learning is adapted to the agent's own body because it's self-exploration, so it abides by the theories of inaction and error and trial, where the robot learns through its own actions. So everything it learns is adapted to itself. It's also good for multitask learning, or choosing which activity, which task you want to play with, which toy you want to play with. But still, it has weaknesses when the explorable space is unbounded. When you have too many tasks, or if your environment is too large, there's too much to explore, and you can quickly get lost. If you explore the whole universe, it's way too large, and if you're not bound to the Earth, if you do random walk on the universe, you most probably are just in the dark between stars and planets, and you won't see anything. You need somebody to indicate where the Earth is to be able to explore the Earth and see something interesting, for instance. If you watch, well, children, of course, they learn autonomously, but they also learn with their parents, with the adults, and with other kids. So this is called social guidance learning, and one of the methods most cited is imitation learning. Different methods have been developed, like keyframe and trajectory demonstration, programming by demonstration, or inverse reinforcement learning. The good thing is that the demonstrations highlight efficient localities where when you have a very big search space. So you pinpoint the right regions that are interesting to explore. But the downside is that the teaching dataset is often sparse and suboptimal. It means that you don't have enough data to cover the whole space. You don't have a few data only that pinpoints a few interesting examples, but it doesn't cover everything. And also maybe the teacher showed you demonstrations, but they are not the best at this task. They show you something that are not so bad, but maybe not the best optimal solution. So how can the robot go beyond the data set of the teacher? The second downside is correspondence problems. So correspondence problems is um, um, how you translate a demonstration from a teacher to yourself. Um, so the robot doesn't have the same body as humans. For instance, we have an arm with a lot of degrees of freedom, but if my robot's arm has only 2 degrees of freedom, of course it cannot do the same movements as the ones I showed you. So how can it translate the movements I just did if it doesn't have the same joints, the same body? And the last downside that I mentioned is that it's for single goals. Mostly the imitation learning is done to explore only one goal, and it's not well developed for multitask learning. But so you can see that infants can explore both by autonomous exploration and social guidance. But when you think about it, actually, this choice of switching between these two strategies of learning is done by the infant, the child itself. Or from time to time, when you go up to a kid and want to play with the kid, he just ignores you because he's so curious and interested and concentrated in his own play. And from time to time, he would be bored by his play, and he will come up to you and ask you to play with him. So the same should go with the robot. The robot should be able to choose to do social guidance or social guidance or autonomous learning, depending on the situation, on its levels of interest. And it can choose that also by intrinsic motivation, what it makes it more curious. So this theory, this psychological theory of intrinsic motivation has been translated in machine learning and robot learning within the reinforcement learning framework. So in reinforcement learning, you've seen yesterday algorithms like Q-learning. You've heard probably about deep Q-learning and actor critic algorithms. The robot learns to try to maximize a reward, a cumulative reward. And this reward is extrinsic. It's the environment that gives the robot this reward function. And the reward is supposed to give a stimulus that is either positive or negative, so as to reinforce or hinder behaviors from the learning agent. And most of the time, this reward function has been designed specifically by engineers for a specific task, so that the learning happens for this specific and long-term goal. In intrinsic motivation, we stay within the reinforcement learning framework, but in this case, the reward function is no longer intrinsic, but it's no longer extrinsic, sorry, but it's intrinsic. Intrinsic means that the reward is defined from variables that are within the learning agent's system. So to translate the idea of curiosity and progress that psychologists have highlighted, the reward corresponds to learning something new. And we propose this definition of reward by using a measure of competence. So let's say the task of the agent is to reach a goal, omega j, let's say this point here. But in reality, it's quite clumsy with its arm, and all it does is reach this point here, which is omega r. So this is the real outcome, and this is the goal outcome. And the distance between the two will be the competence. And if we do several times on several tasks, we can use the mean value and infer the mean competence. And the reward would be progress. So if we do progress in competence, so the difference, the evolution of this competence, then we get positive progress and we get interested. The activity gets more interesting if we do more progress. So this is a definition of a reward value that doesn't use external environment variables, but it uses mostly internal variables, because it depends on the history, how the competence has been on the past for the agent. So intrinsic motivation has been developed quite a lot to learn multi-task learning, to learn a set of skills. It's been used to decide what, when, where, how to explore. We will show some meta-learning algorithms to maximize the informativeness of exploration. So why have I talked about intrinsic motivation, transfer learning, social learning? The first one was hierarchical learning, because if we look at the robot, it should be more than a machine. And one of the conditions is that it should be able to solve different tasks. For instance, in this case, there are several tasks to learn. And the control task is to learn which action to give as command to its joints to be able to move the pen at a specific position XYZ, draw a specific letter A, for instance, or move the agent to a specific position. So which models should work? It needs to learn all of these models, which can be each neural network. So which are the weights of this neural network? To summarize all this, what it does is learn a mapping between a task space. So position of a pen, letter that is drawn, a position of the agent on the screen, and an action space. So a command on its joints. Here, the task is a multitask learning. So the whole task space is the union of different subtasks here. The action space is defined first through an action primitives. So an action primitive is just a parameterized function that gives parameters for its action. So it gives a shape, for instance, of a movement. And here the parameters can be real numbers of dimension n. To be able to, for instance, grab the pen, it can use one of those action primitive pi theta 1, for instance. But then to draw a letter, then it needs first to grab the pen and then move the pen to somewhere else. So you can use a sequence of two primitives, pi theta 1 and pi theta 2. And how about this task? How many action primitives it needs to do? Without domain knowledge, without a priori knowledge, we cannot know how many primitive actions it needs. So we don't know a priori the maximum length of this action. So a priori, all the actions possible is just any list of primitive actions. So the action space is pi to all integers. So it's a infinite dimension space. And the same goes for the other setup. In this setup, given the context, if it needs to go to a specific position, which orders does it need to send to its wheel? So which is the model that it needs to learn? Same for pushing with an object. So in both cases, we're learning mapping between a composite continuous space to a space of infinite dimensionality. The question is how to learn a mapping between high-dimensional spaces and to learn all tasks in which order, and how to learn the relationship between tasks. The background is that for lifelong learning, we need to learn an open-ended number of tasks. And we have very limited resource because there's a huge task action space. And the idea is that we can use intrinsic motivation to explore the task space and the task decompositions, also try different features and discover new tasks.
May I interrupt a little bit?
Sure.
I saw a question in the chat, and the question is, what happens if the robot doesn't feel intrinsically motivated to do something?
So actually, the notion of feeling motivated to do something, as put in the question, is something where you consider that being motivated is something positive. So if the value of motivation goes above a certain threshold to give you the will or the energy to do it. Here, the task of the robot is to learn, so it has no choice. It needs to learn something at each time, and so the question that the robot needs to do is to solve the question. Now I need to learn something, but what do I need to learn, and how do I need to learn? So the motivation, as defined mathematically in the algorithms, is a relative term, meaning we measure progress for each task and each strategy of learning. And we will pick the one that has the highest value. So it's always motivated, or if you put it in another way, it's always less unmotivated by one task. So it picks the one that has the highest value. I'm not sure if you agree with that, but it's I say the mathematical way, algorithmic way of doing this. It's not very literary way of answering the question.
Okay, and I have another question.
Yes.
If imitation learning is only aimed to human-like robots, or it could be to any particular robot? Oh.
No, it can be really to any kind of robots. So you saw here an arm that is a very robotic arm that doesn't look at a human. Imitation learning, we have this idea because of the social context, but it can be also learning from another robot. So if you have a new robot, but you already had another robot that can do a few tasks, maybe the new robot can learn from the old robot. And because maybe they are not the same model, the same type, or maybe just because the old robot is older, so it doesn't perform, it doesn't roll, the motors are not functioning exactly the same way as new robots, then you always have a bit of difference in the action and the effect that it has in its environment. So you always have correspondence problems.
Yep. Thank you very much. I don't see follow-up questions to the answers.
Okay.
Thanks.
So I'll try to go fast on our proposition of a unified active learning architecture for the learner to decide what, how to learn, what, when, and whom to imitate. To learn task decomposition to use transfer learning, and also to discover unspecified tasks to use as a subtask. So first, for a transfer of knowledge from a teacher, or in other terms, imitation learning. So for instance, in this task, the idea is that the robot needs to learn the inverse and forward model that links each action and the effects on, or outcomes on the environment. So if it does this action A1, then it can observe a change in the environment and outcome B1. With imitation learning, it can look at what a teacher does. So a teacher does an action, and maybe it can imitate. So it translates this action into its own motors, commands, and it does this action, and it can observe that it does also a change in the environment, but maybe the change is not exactly the same as the change of the teacher. It can also do emulation. Emulation is when you observe a demonstration of the teacher, you observe both the action, but also the change in the environment. And instead of trying to replicate the action, you try to replicate the effect, the outcome. And to do that, you use your own action. So that's the idea of emulation. So we propose an algorithm where the robot can explore both autonomously by mimicking the actions or by emulating the outcomes and effects. And on all these, they will explore both the task space and the action space. So for instance, in autonomous learning, the robot will choose a task that it wants to solve. So for instance, it wants to solve writing the letter B. So that will be the goal by G. And by using its model, inverse and forward model, with goal-directed policy optimization, it says, okay, to solve this, to write this my letter, I need to do action AR. And when it does this action, the environment will be transformed and it will see an outcome BR. So instead of writing the letter B, maybe it has written the number 6. And the difference between Beiji and BR will be assessed as with the measure of competence J, and it will be used to map the interest in the outcome and sampling space. With mimicry, it will ask one of the teachers for a demonstration, and you will get a task and an action. It will translate this demonstrated action and do a change in the environment. And again, the difference between what has really been seen as the effect and the goal task will be computed as and measured for the competence. The same goes for emulation, where it requests a teacher a demonstration, and this time it uses the demonstrated effect to emulate, and it will choose an action by itself. So either way, these strategies give actions and effects on the environment. And these data will be used to improve and optimize the model, the control model of the robot, to be able to improve its goal-directed policy optimization for the next step. And for the next step, it also will choose between one of these strategies depending on where it makes the most progress, what motivates it most. So to explain a bit more this choice of motivation, we can figure out, for instance, here we have task space that has 3 different types of task. So it's a composite task space, and each has been divided into subtasks, and it will be divided throughout the exploration. And for each subtask, we will record the measures J for each of the strategies of sampling. And we will look where the progress is highest, so where the slope is the steepest. And for instance, here, this is the highest progress. So for the next step, we will try to mimic this teacher here. So throughout the learning, what this algorithm called socially guided intrinsic motivation with active choice of teacher and strategy does is that it will choose by itself throughout the learning. So this is the axis, the timeline axis, the number of actions that it will try out. It will alternate between emulation, autonomous exploration, mimicry, maybe a mimicry from another teacher, then emulation from another teacher. And this choice is done through the progress measures with intrinsic motivation. So what I've talked about now can be applied mostly for simple primitive actions. Now, what happens? How can we take advantage of hierarchical actions when actions are related to each other? So we come back again with our mapping between actions and outcomes. And here, instead of simple outcomes, we can consider that some outcomes can be decomposed into subtasks. And so each subtask can be mapped to an action. Therefore, the complex task of writing a letter can be mapped to a sequence of 2 actions. And we can also be interested in the knowledge of teachers about task decomposition. For instance, to write this drawing can be decomposed into 2 subtasks that the teacher can show. And we can then reuse this knowledge by saying, okay, this, I already know how to solve this, and this, I also know how to map it directly. So that the task of drawing can be solved with a sequence of 3 primitive actions. And it will be mapped to a compound action. So what we try to learn is to learn compound actions using task hierarchy to solve multitask learning with policies of different complexities. So we propose compound actions as sequences of primitive actions of adapted size. And the robot needs to discover and exploit the task hierarchy. And for that, we propose a task-oriented combination of skills as a representation of compound actions. So we call this the procedure framework. So it's a representation of compound actions in a task-oriented way. So we define a procedure as a list of tasks, B1, B2, B3, Bn. Or in other words, it's a combination of sub-goals. And the roller needs to learn to map a goal into a list of two sub-goals, for instance. For instance, here we have the drawing, which is to draw a line between point xa, ya, and xb, yb. Then we need to move the pen to the first point, xa, ya, and then move the pen to the end point, xb, yb. And to reach B, so to draw this line, we need to perform the action sequence A1 and A2, where A1 solves the problem B1 and A2 solves the problem B2. And so the exploration problem is how can we discover the task hierarchy by exploring the procedure space. So this gives an update to our algorithm. So we have this version, updated version, which is called Socially Guided Intrinsic Motivation with Procedure Babbling, which looks like the same way as before, except that now we have a procedure space exploration, and we have new strategies like imitate procedure or explore procedures autonomously. When it's exploring autonomously, it chooses goal like before, and here it will decompose this goal into two sub-goals here. And it will then use a sequence of two actions to use on its environment. And the rest is the same as before. For imitation of procedure, it's the same. It will take a demonstrated task, and it's decomposition from the teacher, and then it will do a succession of two actions, for instance. So on the setup of the robotic arm, what we have is this kind of results. So here on the x-axis is the timeline, the learning timeline. On the y-axis is the distance to a benchmark. So we ask it to reach a few tasks that we have specified before, and we measure the distance between the specific task and what it has really done, the reached task. And our algorithm, SJM ACTS and SJM PB, do quite well, and they make the fewest errors, knowing that SJM PB is better than SJM ACTS. So we can compare it to IMPB, which is the same as SJM-PB, so autonomous learning of task decomposition, but without the without the social learning, the imitation times. And SAG-RAC, which is only the autonomous exploration of the policy and task space. And we can see that adding the procedures, exploration of procedures, and this representation of task decomposition is a great help for learning. And if we add again imitation, then we have a big jump. And imitation of task and actions without the task decomposition is also doing pretty well. If you look specifically for each of the tasks, we can see that for the simple task, which is just moving the end of the tip of the robot, there's no difference between all these algorithms. So there's no advantage to social guidance or task decomposition because it's a simple task. But for more complex tasks like drawing or moving the agent on the computer game, then we can see a more clear difference between our proposition and the other versions. This means that HAMPB learns better with better precision, and there's a clear advantage for complex tasks. And HAMPB also performs better than IMPB, which means that the procedure space exploration alone is not enough, and we need also social guidance. Here we look at how the robot has decomposed its different tasks. So for drawing, we plot the histogram of the different procedures that it has used, and we see that it has decomposed it into moving the pen and then moving its arm. For moving the character, we see that it's not so clear. It has used also other procedures, but mainly it has used moving the red and then the green joystick. So it means that HMPB learns the correct task decomposition. If we look now at the sequence of actions that have been used for each task, here we have the size of the sequence of actions here for each of the tasks, omega 1, omega 2, omega 3, and we have plotted the histogram. So for omega 1, which is moving the end of the tip, so the very, very basic task, it uses mainly sequences of one primitive action, so only primitive actions, which is coherent, it's simple, it doesn't need a very long action. But for omega 2, which is a drawing, a letter, then it uses mainly sequences of 3 actions, 3 primitive actions. So we can see that it uses short sequences of actions for simple tasks and long sequences of actions for hierarchical tasks. Again, if we look at what happens inside and for each outcome space, what kind of strategy it has used for exploration, we can look at, for instance, omega 2, the learning of drawing a task, and we see that it uses mainly teacher 2 for mimicry and procedural teacher, which means that it learns that the other teachers are not so relevant because they are teachers for the other task. So they're not relevant for this task. And that for this task, which is difficult, which is a hierarchical task, it's better to learn the hierarchy with procedures. It's more useful than just trying to mimic actions. So HRMPB learns the teacher's domain of expertise, and it chooses correctly between procedural and policy teachers. So we also apply the same algorithm for industrial robot arm to learn a complex task. So it can perform simple tasks like reaching a point, but it can also complete more complex tasks like producing a sound using the different buttons on the DJ table. Here it will emit a sustained sound. For that, it needs to move the blue button and the green button. So each of these subtasks is a composition of 2 actions, 2 primitive actions. And then it can touch another button to make the sound sustainable. So as a conclusion, we can see that we have proposed through the procedures a goal-oriented representation of compound actions. This contributes to hierarchical reinforcement learning as procedures enable the discovery of task hierarchy through exploration that later enables transfer of knowledge from easy tasks to complex tasks. In terms of curriculum learning, our algorithm can choose to learn easy tasks first before complex tasks. And it also chooses the most adapted teachers for each task to ask help from. In human demonstrations, imitation learning, we see that it can bootstrap the learning. First, because demonstrations of procedures help a lot, especially for the high-level hierarchical and complex tasks. We show that our algorithm can decide what, when, how, and whom to imitate. It can learn the domain of expertise of each teacher, and it can choose to imitate either the actions, the task, or the procedures. So what we've seen is a good case of discovering the different subtasks, but the relationships between tasks. But for now, what we've seen is that all the tasks are already given in advance. What happens if the subtasks are not given in advance? How can it discover that these subtasks exist and learn them before completing more complex tasks? So let's come back to this example setup where the robot has to learn how the actions on its wheels will affect the positions of objects that it will push. How can it push an object with another? Well, a simple idea is that before mastering this, it could learn to first control its own position. So generally, in hierarchical learning, you need to learn the features of each of the submodels, but the task of robot position is already given and is already on the list of things that you need to learn. Here we say, okay, we don't know that this is a task to learn. The robot can observe this, but it doesn't know that it needs to learn it, and then to reuse it as subtask. So how does it do? Here in our environment, we have, again, actions that can be successions of primitive actions, and each primitive action is a two-dimensional continuous parameters. And it has observables. I can observe where it is, the displacement it has done, and also the positions of the object on the table and the readings of its lidar. The robot explores its environment by episodes in an active manner, and the acquired skills are tested against the test benchmark of all possible outcomes. So we'll try to see if it can move itself in any place in the room, and the objects also, if it can move them in any position in the room. To solve this problem, we propose an algorithm called CHIME for continual hierarchical intrinsically motivated exploration. And how does this algorithm work? What does it know in the beginning? So it knows that it can perform primitive actions, like moving the wheels at a given speed. And it can also retrieve the current value of observables, like the position of the robot, the position of different objects, etc. The colors and the physical sizes of objects. So what's the purpose of CHIME? What does it learn? Well, it learns like before, how to achieve a task, to learn the mapping between an effect on or an outcome in the environment and which actions it needs to use to have this effect. It also learns what it can control, what it can achieve, what tasks are there to learn, which are the controllable effects and which controllables are not related to its actions. It also learns the inputs of models. So if there are dependencies or between tasks, for instance, if task 1 is influencing task 2, and effect 1 is influencing an effect 2. For instance, the position of the robot is influencing the position of objects if it's pushing the object. And so what are the main principles for Chime to learn? First, it uses intrinsic motivation, like the algorithms before, based on performance progress as an active learning measure to choose what to learn, where to explore, and how to explore. It also uses planning for exploitation. So let me go into a deeper detail about this algorithm. The robot just first selects an affordance and it generates a goal. For instance, an affordance is its own position or the position of an object. Here it tries to reach a position Beiji that is a coordinate xy, for instance, in the room. And once it has done that, it selects a valid object. So here it's itself, the robot, or it can be for an object A or an object B, a small object or a big object. And then it plans and executes the task. So for that, it needs to use the model of moving the robot. And it will infer a command A, an action A that it sends on its wheels. And when it does that, it moves and reaches a point BR, which is the real outcome or effect on the environment. Then it can, from this data A and B, R, it can update its model of affordance. From that, it can also measure the difference between BR and the goal task, which was Beiji. And from there, it can have a measure of competence, which is the distance between these two, and update its intrinsic motivation. And then for the next task, it can then either do some random exploration or choose another model or another task. To learn this, it can observe actually its own position and the position of objects. And it tries to relate to its own actions, which is the action primitives of the wheels. So first, it can learn that the wheels relate to its own position. So it creates a first model, which is moving the robot. And when it comes across an object, it can see that it can move the object, and that the position of the object is actually related to the position of the robot. So the model moving an object takes as input the robot position and outputs the object position. And so it learns through these submodels to push an object with another through the commands of its wheels. So this uses a hierarchy of affordances. It also can use affordances multiple times in order to use a sequence of actions. Let's say that, again, it wants to move an object. Then it uses the model moving an object, which uses the model moving the robot. And this outputs a command on an action A on its wheels. And it can reach the object and push it. But what happens if the object is very far? In one time step, it can't reach the object. Then we need to use a planning process. It uses the model of moving the robot several times so that the robot can get nearer and nearer the object to reach it. Here are the results of our experiments when we asked the robot to reach different positions in the room or push the objects into different positions in the room. We have plotted on the x-axis the timeline of learning, and on the y-axis the task evaluation. So here 0 means that it's doing bad and 1 means that it's doing very good. And we can see that for the task of controlling its own position, it learns it quite quickly. And by 300 iterations, so time steps, it has learned to control its own position. The model that it learns says that the robot's position is directly linked to the control of its wheels, but it's also related to the LiDAR reading to detect if there are any obstacles around. The second model, which is controlling position of an object, the model M1, comes in later, around 1000 iterations. And here, the outcome is the object position, and we can see that the inputs is the robot's position. So it learns to link directly the object position to the robot position. And it means that it can reuse the knowledge that it has on controlling the robot position. And it's only later that it learns to push an object with another object, which creates a new model here, around 1,500 iterations and 2,000 iterations. The learning curve is increasing. So we can see there that through these results, the robot learns multiple tasks. It learns also its curriculum because it starts by mastering its own position, which is a simple task, and it's only at the end that it tries to push an object with another. And it builds the hierarchy between tasks, and it can reuse directly the actions for each subtask to control the bigger task. So last, we'll compare the performance of our algorithm to other methods like Q-learning, deep Q-learning, active critic, or another algorithm called Curious, which also uses intrinsic motivation. And for the first task, we see that our algorithm learns it quite quickly, around 200, and the other algorithms learn it around 10,000 iterations. So it comes much later. For the second task, which is pushing an object, most algorithms here also learn 15,000 iterations, but we can see that there are a few, like the non-guided Q-learning and deep Q-learning, that cannot perform because their reward functions are too sparse. And on the last task, we see that all algorithms cannot do anything. They cannot learn to push an object with another. And only Curious, which is also another algorithm with intrinsic motivation, can learn, but much later than our algorithm. It learns it around 15,000, 20,000. Chime learns much faster than the other algorithms, and it has a clear advantage, especially for the complex, the high-level hierarchy task. To summarize, Chime could discover tasks, and it can also discover the hierarchy of tasks. It learns to control multiple objects based on physical properties so as to generalize to new objects. It also is a way of using sequences of actions in a manner that is temporally abstract. So there's no clock to tell how long the actions should last. The limits of this approach are still that the sequences of actions are not learned, they are inferred by planning, and it cannot adapt efficiently when a task itself changes yet. Of course, because it uses planning, it might be having some difficulties when the planning is slow. Therefore, then the Chime algorithm is also slow. So I would now like to illustrate how actually we can use such models not only to enable robots to learn, but also to model and understand cognitive science, for instance, child development. So I'm going to illustrate how we can model the development of vocalization, how children, infants, can learn to control their vocal tract and their mouth to produce sounds and to be able to speak. So for that, how such a model can be learned to associate a sound that we want to produce and the command on the vocal tract and the or the mouth muscles. And using the algorithm SJAM-SCTS, we had our system learn both autonomously and with social guidance, meaning with sounds in their environment so that they can emulate. So what we found out is that there are 3 families of sounds that were produced by autonomous babbling exploration. The first is no phonation, then there are unarticulated sounds and more articulated sounds that resemble more like phonemes. So I'm going to play back these sounds. So you can hear them. The first was not very articulated and the last one was more articulated. What we found also is that if we put sounds in the ambient environment, we see that the system actually does mostly self-exploration first, and it's only in the second phase, once it has been able to produce some unarticulated sounds, that it starts trying to emulate the sounds that it hears. So what we found, it correlates with what has been described in infant development of vocalization. What we found is a development from no articulation to articulated sounds, and a development from no influence of the ambient language to imitation of sounds of the mother tongue. So as a conclusion, I'd like to say that we have presented learning algorithms in various forms for multitask learning, leveraging hierarchy, leveraging discovery of tasks, where we showed that intrinsic motivation, and in particular competence and competence progress, can be used to choose the best transfer of knowledge possible. We have presented SJAM and CHIME that constitute algorithmic framework for learning multiple control tasks through curriculum learning by discovering the dependencies between tasks and exploiting this hierarchy to transfer knowledge from the easy task to the compositional task. In terms of hierarchical reinforcement learning, we have proposed both with CHIME and the procedures, temporal abstractions of sequences of actions. And we showed that our algorithms can learn the discovery of task hierarchy. And that it can use that to transform knowledge from easy task to complex task, either through the procedures or task decomposition or planning. In terms of curriculum learning, our algorithms, CHIME, could discover tasks that were not specified to learn in the beginning, and both CHIME and SJAM could choose easy tasks to learn first before tackling more complex tasks. In human demonstrations, imitation learning, we show that demonstrations can bootstrap the learning. And our algorithms can choose the most adapted teachers for each task after learning, understanding their competence domain. And therefore, it can choose between imitation of policy, outcome, or task decomposition for imitation. It can also choose as a whole what, when, how, and whom to imitate. So it can spot who is the best teacher for such task, and also for that task and that teacher, is it better to ask them to give demonstrations of policies, movements, actions, or of task or outcomes, or of task decomposition or procedures? So thank you for your attention. I put the main articles that have been cited in this work.